Alright, hello and welcome to the next week of lectures. So we're going to talk about logic, circuits, and binary, oh my, in this set of slides. We won't get to binary today though. That'll be for next week. So the idea is we're trying to learn how to write a good argument. We want to prove things and have people listen to us, so we need to learn how to think logically. We'll start with that. And then we will discover some applications of logic in computer science, because this is a computer science class after all. So yeah. Here's what I want you to be able to do, and let's get started talking about logic and how to prove things, how to understand what's true and what's false, because that's what logic is all about. We want to prove true stuff and not prove any false things, okay? That's the idea. But because this is kind of half a philosophy class, we should probably take a second to step back and try and figure out, well, okay, I want to prove true stuff. Well, what does true really mean? Some people have different definitions of truth, and we'll talk about a few of them. Okay, so what even is truth? That's going to be very necessary to go over before we can prove true things. So let's get started. Here are some definitions in logic, and the first one is of statements or propositions. And don't think of like the English definition of statements. This is like logical statements. Okay. Is the definition I'm about to give you, because it's very different to like what you would look up in a dictionary and see under statement. Okay, so we're talking about logical statements, and they're also called propositions, and they're just sentences that you can write in English that can be true or they can be false. Okay, so one or the two, or one or the other. They cannot be both true and false at the same time. That would make absolutely no sense at all. And so, unfortunately, there are statements, there are sentences that are not statements, that are not propositions, and here is one of them. If I tell you this sentence is false, you have no clue what I'm saying, because it's not a statement, okay? A statement's supposed to be true or false, but this one can't be either, and I'll show you why, okay? So let's work under the assumption that we have these two options to choose from. So either this thing that you're telling me is true, or this thing that you're telling me is false. So in either case, I have made my choice. It has to be one of these, right? Well, this one can't be any because of the following reason. So let's pretend that you're telling me this and you're telling the truth. So we're in this case. Well, if this thing that you're telling me is true, that means this sentence was actually false. Okay? So if I just assuming you told me the truth, I have to conclude that you were really telling me a lie. Okay, I hope you see that. It's a weird twist, but it does make sense. So if you assume that this sentence is true, if you were telling the truth, that means it was really false. Okay, so it made no sense for it to have been true. I must have been wrong. Okay, so maybe it was false. Maybe this sentence is false. Okay. So if this thing between quotes was false, that means that, it's hard to say in English, it means that this sentence is false, which means that it was really true. You see that? So in either case, like, okay, if it was true, then it must have been really false. Well, if it was false, well, then it must have really been true. We're going back and forth here, and this is called a contradiction. Okay? That means it was neither. So under the assumption that it was true, it was really false? No, that makes no sense at all. So this is not a statement, it's not a proposition. So sadly, we have just disproven our hope. We would really like to be able to prove all the true stuff in the world and disprove all the false stuff. Okay, but some things come along that look like this, or we are just incapable as humans of proving, unfortunately. There are some mathematical facts about what we can and cannot prove, and we cannot, unfortunately, prove all true things. It's quite sad. But it's a good wish, right? It's a good hope. Well, maybe we should think of truth then as things that we can prove. Maybe that's a good starting point. Maybe we should define truth to be provable things, okay? So that's where I'm going with this. And there are a few competing ideas about what truth should be, and I'm going to talk about 4 of them. Okay, I'm going to give you those definitions, and we'll see which one clicks the most for you. Okay? So the first thing that I want to talk about, the first theory of truth, is called correspondence theory. And this is probably one that you use in your everyday life. So it's a good place to start. So we'll say, well, let's define truth as, well, okay, a statement S. We're using variables because we're getting mathy. We'll say that a statement or proposition, if you call it S, it's true. S is true if and only if S corresponds to a fact. Okay? So it's a bit not fun to discover what it means to be a fact, because that's just another rabbit hole to go down, so let's not go there. But let's pretend that a fact is something that maybe you can see, something that is real. Okay? So someone's like, all right, yeah, the grass is green. You can go take your magnifying glass, look at some grass, and be like, oh yeah, checks out. That must have been a true statement. Okay? So true things, we say, correspond with reality. And again, things like, okay, yeah, snow is white. That's a true statement because I can go drive up to China Peak if I wanted to and look at the fact that, yes, snow is all white up here. Okay? So things that are real should be true. Let's say that. That's a good definition, right? Well, some people think that there are different ways to prove truth. Okay? Correspondence theory is not everything. Because maybe like we're proving mathematical things that we can't look at. Okay, so how do we get farther? How do we go deeper? Okay, so there's another theory of truth called coherence theory that you might want to use. And there's actually a few, which is weird to think about. There's a few coherence theories, but here's one of them. Okay, so the coherence theorists define truth as, okay, a statement S is true when it matches other true things. Okay, so I know some true things, I'm bringing together true things, and I'm building up my knowledge of what is true. Okay, so there's this concept of building things up. That's a G, up. Yeah, just old knowledge, or new knowledge from old knowledge. Okay, so for example, this is good for math because it's like, okay, 2 plus 2 equals 4, that's something that you can't like look at very easily. We have to define things in a different way. But we can say that this is true under coherence theory because we know what 2 means, we know what 4 means, we know what plus means and how it works on numbers, and we know what equals means and how it relates to numbers. Okay, so we know all of those different things because they're made up of all those different parts. There's my 2's, my pluses, my equals, and my 4's. I know what all of these little characters mean, and I know what's true about them, and I can build up this statement and prove that it's true from that knowledge. It follows from it. Okay? That is the idea of coherence theory. So that's one coherence theory. It's the nicest one, I think. There's other kinds of coherence theories. It's like, okay, we'll define that S is true because it matches the beliefs of the majority of people in my society. And I think we could see very easily that that is a huge issue, or it could potentially be one. Okay, so that is coherence theory of truth. That's another definition of truth. There doesn't have to be just one. Maybe you use coherence theory for some things and correspondence theory for other things. And there are more than just the 4 that I'm talking about, of course, as well. So the next one is called deflationary theory, for some reason. It's called redundancy theory as well. And this one, I don't really understand that well because I'm not a philosopher, but I'm going to try and relate it to you. So redundancy theory, or deflationary theory of truth, it doesn't define truth at all. In fact, it says that you shouldn't be defining truth. That makes no sense. Okay? Saying that, okay, yeah, 2 plus 2 equals 4 is true is redundant. Just say 2 plus 2 equals 4. You never had to use the word true. So it makes no sense to define true because you don't need to, is what they're saying. That's the idea. There's no reason to understand what truth is because it's just what is, if that makes any sense at all. Truth doesn't exist. Okay? That's their point of view, and kind of goes around everything we're trying to do. So I can tell you right now that I don't fully understand it, but I want to show it to you because there are some people that disagree in this realm of philosophy. Okay? Another one that is interesting, again, is called pragmatic theory. Okay, so they define, the pragmatic theorists of truth, they define truth to mean that, okay, something's true if it's useful to believe. Oh man, that's not a good thing sometimes. Okay, so to them it's all about utility, and our boy John Stuart Mill is quite happy with this definition of truth, I would think. So, yeah, it's just a belief is true. They say that it's true if it leads to the best payoff, okay? So it's pragmatic for you to believe this thing, okay? It's going to be the best justification. It's going to promote success. Any of those things, well, we might as well take them as true, okay? Because they're going to help us, okay? So that's what the pragmatists think. And so, for example, one possible pragmatic truth is, okay, I'm totally, always, definitely, if I go out, I'm gonna get COVID. If I go to that party, I'm gonna get COVID. Okay, it's going to happen. When in reality, maybe it won't. Okay, it's quite possible that it won't, but it's still a very good thing to assume to keep you from going to the party. Okay, it's probably better for you in the long run to not do silly things during a pandemic. Okay, so that is pragmatic theory for you, and I am almost certain that you are even more confused than when we started. So don't worry. Again, this is just to make you think, to get you confused, to make you make your own choices in the world. So all I want to say as we're going forward is there is no right answer, again, just like in your essays. You can pick any one of these, and as long as you argue it well, it was the right choice. Okay? So that is philosophical truth. Let's get back to something that I am very good at and I understand. Computer science truth. Okay, so there's something called Boolean algebra created by our boy George Boole that we talked about at the beginning of class. We can use this to do cool computational stuff and to kind of sidestep. There's a concept of truth that is kind of universal, and we'll talk about that here. All right, so the kind of question that I will answer in this section, hopefully, is how can we formally specify statements? Because English is horrible. Like, you saw how much I fumbled trying to even reason about this sentence, and it was because it was in English, okay? So there's a way that we can formally specify things that make it easier on us, all right? So here is my motivation for you. Let's pretend you're at a restaurant. Wouldn't that be nice? And your waiter says, okay, you can have cream or sugar. And the assumption was, okay, here's my little cream packet. The assumption is you can actually have both if you wanted to. And here's a little sugar shaker. Got that little thing. So you can totally have both under this circumstance, okay? I'm trying to motivate to you why we should use something other than English right now, because I'm showing you two different ways to interpret the word or, okay? That's where I'm going with this. The other interpretation is, okay, another situation where you could hear the word or is, you're done with dinner and mom says that you can have a cookie or ice cream for dessert, okay? And I'm pretty sure you understand, if this happens to you, that you cannot have both, okay? You can have one or the other. You can have your ice cream or you can have the cookie, but you cannot get both, okay? So, English, why'd you do this to us? There's or twice, meaning two different things. What is going on here? So, if we jump to logic, to formal logic, we do not have this problem because we can make two different kinds of ors with different symbols that do not confuse us. All right? So here is the first way of defining or in logic. Okay, it's called inclusive or, and we give it a special symbol so that we don't confuse it with anything else at all. Okay? So here's the idea. If you want to prove that A or B is true, and remember, maybe our example is cream or sugar. So cream could be A and sugar can be B. We just have to show that A is true or B is true or both of them are true. Okay, that's what it means for an inclusive or, cream or sugar. to be true. All right, so this is called a truth table, and it shows us all the possibilities and when this thing that we're defining is true or false. Okay, so you'll get used to it, I promise. This is a truth table. Okay, and the idea is the waiter tells you, okay, you can have cream or sugar. And we're saying, under the inclusive OR definition, that this is a true statement in any of these three cases. Okay? It was true for the waiter to say, yes, you can have cream or sugar. If they really did have both in stock, then it's still true. So A or B, cream or sugar, yes, that was a true statement. You totally can have cream or sugar under the inclusive OR definition. Alternatively, maybe they were secretly out of sugar and the waiter didn't know. We still define inclusive OR to be true in this case because it's like the waiter said, okay, you can have cream or sugar. There is one available, and so it's true. Okay, so it's a bit weird to think about, but it will make sense when we talk about it further. Finally, the other option, the other way for this to be true, so the waiter's still telling you, okay, you can have cream or sugar. Maybe they're out of cream and they only have sugar. So we say under the inclusive OR that is still a true statement because you can still have one of them. So in order to prove A or B with inclusive OR, you just have to show one or the other. It's okay for them to have both, though. Usually we interpret them to have both. Okay, the one time it was a false statement was when they were out of both cream and sugar. Then the waiter shouldn't have said to you, yeah, you can have cream or sugar, because you can't have even one of them. All right? So that is inclusive OR. That's one way to get rid of this horrible English and define OR to mean something that we can logically agree upon. Okay, so you need at least one or the other. So just A works, just B works, having both of them also works. So that's what it means for inclusive OR, to be true/false. On the other hand, here's the other kind of OR that's popular. It's called exclusive OR XOR for short, because they like that. Just bring the X out. It has its own symbol. It's like a little plus with a circle around it, if I could draw that well. That's what it looks like. So maybe it's like an X turned sideways and then O for OR. That's the idea. So in order to prove A XOR B is true, then you just have to prove that you have A or you have B, but not both. So this is the other side of the coin. So here's the cookie, here's the ice cream, and here is mom saying you can have a cookie or you can have an ice cream, but you can't have both because this is exclusive OR. All right? And so the way to think about this is, okay, was mom lying to me again? Okay? So you can have a cookie or ice cream, but you can't have both. Okay? So under the definition of XOR, exclusive OR, this is only a true statement in these two cases. All right? So mom is saying, yes, it's true that you can have a cookie or an ice cream. Exclusive OR, though. So it's true in this case when, yes, you can only have the cookie, but you can't have the ice cream. All right? So one is true, the other is false. Alternatively, the one could be false, the other could be true. You can have the cookie, you can say no to the cookie and yes to the ice cream. Like, yes, I'm gonna have the ice cream for dessert. Thanks, mom. And so it was a true statement again in this case. All right? So in order to prove that A XOR B is true, you just have to prove that it's true when they're opposites of one another. You can only have one, but not the other, and not both. In these two cases on the outside, this is the one case that makes it different from inclusive OR. It's saying that, okay, if you had both, no, that was actually a false statement. That's not what XOR means. So mom was secretly lying to you. If you really could have both, mom was lying to you, and she was also lying to you if you couldn't have any of them at all. Okay? So again, think about it in terms of who is lying to you. Think about truth in terms of whether or not someone's lying. Like, was that statement really true that they just said? All right, so that's OR. That's the hardest one to think about, and now it gets easier. So let's talk about AND. So there's an AND operator in logic. It's the other way. It's like an OR flipped around. So it's like it's really a capital A without the little dot right there. That's all. That's how we say and. So this is A and B. And to prove that A and B is true, you have to prove A and B at the same time. So and actually makes sense in English and logic at the same time. So maybe the waiter is saying, we have cream and sugar. There's probably a better way to state this, actually. We have cream and sugar. There's one example. And so this was only a true statement. The waiter was not lying to you, only if they really do have cream and sugar at the same time. So that's what it means for A and B to be true. All right? The waiter was lying to you in every other case because he used the word and. All right? If there was cream but not sugar, or there was sugar but not, if there was cream but not sugar, or sugar but not cream, then the waiter was lying. And also, if there was none of either, the waiter was also lying. Okay, so the one time that A and B is true is when both A and B are true. So we're logically talking about what it means for something to be true. We're defining truth logically now. Okay, and I hope this is making some sense. Please yell at me if it's not. Again, I'll have more examples after I finish defining these. So the next one is called not. All right, so not is the simplest one because it just takes one thing, only A itself. So to prove that not A is true, you just have to show that A is false. That's the idea. It's a flip-flop. So you can the symbol for not is like this, and I want you to think of it as like a diving board that some person is about to jump off and do a flip on because it flips true to false and false to true. All right? So the only time, like, okay, maybe someone's saying we don't have cream. Maybe that's what the waiter is saying. So that means A is cream, and this is not cream. So the waiter is saying not cream is true. It takes a while for that to sink in your brain, but he's saying that the negation of something is true, okay? It's not true that we have cream, okay? So the waiter wasn't lying to you, only in the case where, yeah, there was no cream in the pantry. Cream was false, okay? Alternatively, if they really did have cream, and he was just trying to save it for the customers that bought more things and are going to give him a bigger tip, then he was really lying to you, okay? That's the idea. Okie dokie, so that's not, and this is where we get to take a step back and marvel at these things. So I should say inclusive or here, because it just so happens that no matter what you're trying to say on the right-hand side, like, okay, no matter what sentence you write, you can put anything there, you can actually express every truth table, everything under the sun, with some combination of and, inclusive or, and not, which is really interesting to think about. Okay, so you just need this. You can use and, you can use or, and you can use not. All right, so let's figure this out. Let's construct XOR, exclusive OR. This thing that I'm telling you is superfluous. We don't need this. We can just use and, not, and or to define XOR. So weird. We didn't really need it. So let's construct XOR using and, or, and not. And I am not going to force you to figure this out and try all the possibilities yourself. This is XOR. So A XOR B is actually equivalent to saying not A and B, or A and not B. Okay? So that's equivalent. And remember all these symbols. This is XOR, this is not, this is and, this is or. Okay? So I'm going to prove to you using a truth table that these things are equivalent. So they're columns of the truth table. They line up perfectly. It's wonderful. All right, so here's how I'm going to do it. I'm going to make a big truth table for you. So I have my A, I have my B, and I have their possibilities. So we know what they get to be. It's they could be true, true. I'll use capitals now just to save myself. They could be A could be true and B could be false. That's one way that the universe could go. A could be false, B could be true, and they could both be false. Okay, so I'm going to show you, I'm going to make a truth table for this thing, and show you that they're equivalent. All right, so in order to figure out what in the world this is, let's break it up, right? So let's do not A because we need to use that. Let's do not B because we need to use that. So let's make some more columns, is what I'm saying. So let's do not A, let's do not B. We're going to need to use those. Then we'll need to use A and not B. That's the next biggest thing. Not A and B, excuse me. And we can figure that out by using and with this column, this row, and this row. Okay, that's the game that I'm about to play. And then we'll do the other one. That's how we can build up the whole thing. A and not B. And then we'll do the huge thing. Not A and B, or A and not B. And then finally, way over here, we can finally do A XOR B. And I'm trying to show you that these are equivalent. Okay? So let's get there. Slowly but surely. I do encourage you to pause the video and try this out yourself after I do this first one maybe. Try and give the rest a go. All right, so not A, it's just like, okay, if A is true, then not A is false here on this line. Well, A is still true. Not A is false. A is now false in this column, in this universe, so not A must be true on this line. Okay? Yeah, so that's not A. Try not B. If you're back, let me show you it. True, false, true, false, true. And just flop them. Flip-flop them. Flip-flop B this time. And now that I have not A and I have B, I can combine them together using and to figure out the bigger thing. All right? So I'll now combine this one and this one using and. So false and true. Well, it's only ever true if they're both true. So bloop, 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 bloop. They're both true in this case. All right, for this one, it's going to be pretty similar. Probably is symmetric in some way. So we got our A and we got our not B. So true and false, that's false. They both have to be true for it to be true. True and true, hey, hey. False and false. False and true is false. Oh, shoot. I accidentally wrote true right there. This is the one case where it's true. True and true. All right, so that is that. Now we have not A and B and A and not B. Oop, I'm back. My alarm went off. Sorry about that. So now we have both of these. We can OR them together. Finally, just pretend that this whole thing is the A. Pretend that this whole thing is the B, and now we're going to OR them together. All right. So go back to our inclusive OR, of course. So if they're both true, it's true. If one's true, the other's false, it's true. As long as one thing's true, it's true. So in this column, they're both false. So we got darn false. This column, oh, one of them's true. Hey, hey, true. Similarly, true and false. Okie dokie. So what is A XOR B? I think you might remember. It's true and they are different. But not both are true. And oh man, what do you see? I'm going to make this rainbow for you. We're proving that these are equivalent, and they are equivalent, in fact, because look at this. Look at false. Oh, matches with false. Look at true. Matches with true. Look at true. Matches with true. Look at false. Matches with false. So we have proven beyond a reasonable doubt. We've proven perfectly that these truth tables line up. So this is equivalent to this, and life is good. All right? So I hope that was fun. That was truth tables and logical operators. All right. Don't actually need that. There are some more that I don't want to get into for too long. It's just they're interesting in themselves. There's one called NAND and one called NOR. And because, of course, you can use not and OR to define everything, a NAND B, that one operation, we define it to be dun, 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 the not of A and B. So first do A and B, the not it, true becomes false, false becomes true, of course. Then you get a NAND B. You may have heard of the word NAND gate before if you are into technology. NOR is similar. It's not A or B. Okay, so do A or B first, then negate it, we say. So that is NAND and NOR. And the cool thing about these is if you make a circuit that just does the NAND operation on A and B, we'll get to talking about what those mean in just a second. Actually, NAND by itself, NOR by itself, is functionally complete. So you can make any truth table. Using a combination of only NANDs. Okay? So just NANDs. And similarly for NORs. Okay? So these are similar to the whole thing, this whole set of not, or, and inclusive or. So all of these make all the truth tables, and we like to think about things in terms of them, but actually you only need one. If you just define NAND to be this, you can define not and or and in terms of NAND. And that's beautiful. That saves you money because you only have to write one thing, print one kind of circuit. All right, so that is NAND and NOR. They're functionally complete, we say. And then finally, let's give ourselves one last example to drive home everything. So let's say mom says, I will give you $20 if you clean the bathroom and mow the lawn or do the dishes. So look at the parenthesization here. So clean the bathroom is outside of it, and then these two things are ORed together. So if we call this, I don't know, A and B and C. So A is clean the bathroom, B is mow the lawn, C is do the dishes. It's saying A and B or C. Okay, so this is how the parentheses go. And we want to figure out what are the conditions that require us, or under what conditions are we required to get $20 from mom? Is she not lying to us? Okay, so all we have to do is make a truth table. So again, we'll say that clean the bathroom is A, and mow the lawn is B, and do the dishes is C. And so we're really doing A and B or C, and we'll just make a longer truth table now, because we have three things, and they can all range between true and false. So you have to try all those possibilities. And so let me write them out for you. Feel free to fast forward. That's one of the beauties of this semester. You can just fast forward when I'm doing slow stuff. So we got your, I'll actually just do it like this. True, false, true, false, true, false. There's a standard order of these things. As long as you do all of them, it doesn't really matter. True, true. Please line up. True, true, false, false. True, true, false, false. And true, 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 true. False, 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 false. Okay, so that's all the possibilities that A, B, and C can be at the same time. And now, let me do A and B or C, because we want to figure out what's the minimal amount of things that we can do to get money. Okay, so B or C is one thing, and then we'll combine B or C with A using AND to make one last big thing. Okay, so I think you see the game that I'm playing here. Just remember your truth tables, your original truth tables, and you can build up anything that you want to say. Figure out what conditions make it true, what conditions make it false. So I'm going to go a bit faster now. B or C is true whenever one or the other is true. So I got a true there, true there, true there. Oh, they're both false, false. True, 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 false. Okay. Done, done, done. Now we want to AND these with A, and this with A. So they both have to be true. So I've got some trues up in here and here. Where are the trues for A? Oh, they're only over here. Okay? Well, maybe I can do that. So it's only ever going to be true in these first, looks like 3 cases. Dun, dun, dun. That is the idea. So, yeah, because otherwise it is going to be false in at least one. And so I'm going to put, 5 more falses. So only, and now we figured it out. All right, if mom's not lying to us, and this really is true, she's gonna pay us money, here are the different ways that I will get 20 bucks. Either I can be the best son in the world, and I can clean the bathroom and mow the lawn and do the dishes. They're all true. I'll definitely get 20 bucks in that case. Or I can be lazy, okay? I can choose one of these other two options. I can clean the bathroom. I'm forced to clean the bathroom, notice. Okay, that's what the and implies. I'm forced to clean the bathroom, and I get to choose one of these, okay? I can do one or the other or both, because it's inclusive or. All right, so I can just do one. I can mow the lawn and clean the bathroom, but not do the dishes. Okay, you see how those all line up? And likewise, I can clean the bathroom and not mow the lawn, but I'll do the dishes. Okay, so in all those three cases, I'm getting 20 bucks, and assuming mom didn't lie to us, that is. All right, so that is the name of the game. So that is a nice little example that just summarizes everything we just learned. We're learning to go from English, which sucks, to logic, which is nice and not confusing. Okay, there's no contradictions. Everything is only interpreted one way in logic. And now we're ready to use logic to build cool stuff, to build computers. So let's talk about logic gates, and circuits. All right, are you prepared? So I guess I'm going to try and answer this question for this little subsection here. Yeah, logic is awesome. We can specify things without having to use English, but what good is it? How can this help me in my computer science career? What can I do with it? So let me introduce you to the logic gates. It is a little family of different kinds of gates that can be put together to build a giant circuit. Okay, so this is the idea. Every logical operation that we talked about with its own little truth table, A and B, and A and B, for example. You know how it had true, true, it was true, true, false, it was false, 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 true, it was false, 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 it was false. Well, what if you made this in electronic form? If you sent in on the A wire a high voltage, and you sent in on the B wire a high voltage, this circuit might output a high voltage for truth. Oh, and similarly, if one of them was a low voltage, doesn't matter what the other one was, high or low, you're getting low at the end. So this is how we translate from math paper land to digital logic land. Okay, these are circuits. So, yeah, how do I want to say this? So true is equivalent to like a high voltage, a 1, if you will. F is equivalent to a low voltage. And you'll learn more about this if you take a physics class or an electrical engineering class. But as far as I want to go is saying that, okay, you can put enough transistors together in certain ways to make all of these different, we call them logic gates. Okay? And they take just as many inputs as the operation that they perform does. So for example, I'm going to pick on the AND operation. It takes something on the left of the AND, something on the right of the AND, in digital logic form. So these are wires and voltages are coming in and going out. And when we make this shape, we mean we have an AND gate. Okay? This is called an AND gate. All of these are called gates. The NOT gate, the NOR gate, etc. Okay? Now, the output, so these are the inputs over here on the left, and we generally write it from left to right because we read from left to right. The output, there's just one. Well, it's the result of A and B. Okay? That's the idea. And true is high voltage, false is low voltage, and it obeys everything that we expect it to behave, that we expect it to obey, that is. And we have all of these options. So here's the AND gate. It takes two things and then it ANDs them together, and the output is the ANDed form of the answer. Here's an OR gate. It looks similar to the AND, but it's kind of like curvy on the left side instead of flat and straight. And then the NOT gate is also sometimes called an inverter. because it flips bits, it inverts them. Okay, it negates them, and it inverts them. And so you can kind of think of this little circle right here as where the inversion happens, I guess, because NAND is drawn like this, because it's like, okay, then first you do the AND, then you do the NOT, is the idea. Okay, so I want you to just save in the slides where this is, because you'll probably need it later for like the midterm or something. But that's as far as I want to go with these gates and explaining them. Now I want to use them to build up circuits. So let's pretend we were given the proposition that looked like this, okay? Somebody's telling you, all right, I want you to create the logical circuit for not A and B, or C and not D, and of course respecting all the parentheses. So we're gonna do this part first, and this part second, and then we do an OR, and inside of this first part we do the NOT first. Same with over here, so I hope you see how it's all parenthesized. And the idea is, instead of making a truth table, let us build up this circuit using these logic gates. Okay, this is something that I want you to know how to do, right? And it just so happens that we can build up entire computers from just these logic gates. Okay, so the first thing that you do when you're trying to make a circuit from a proposition, so we're trying to do this. We're trying to go from a proposition or a statement to a circuit. Kind of the first step is extract all the variables, okay? Find all the variables, because those will be your inputs, okay? All vars become your inputs. All right, so I'm going to have wires coming in for A, for B, for C, and for D. Okay, they're bringing in whatever the signal is that represents true or false. Okay, and so we now need to build up this circuit. So the first thing, let's just do it in chunks. This first parenthesized thing deals with A and B, so let's deal with them. Let's create first not A and B, and then worry about ORing it with the rest of this thing over here. All right, so to make not A and B, we're going to need an AND gate, bringing together two things of B and eventually almost A, but the negated form of A. Okay, so that's what we're going to do. So the first thing that we're going to do is negate A, so that we have not A. Okay, so now sitting on this wire, coming out of it, is not A. Okay, that's how I'll write this, just to make it clear. Now, we want to combine those. So we want to create not A and B, so we'll use the AND gate to combine B and not A. And remember, the AND gate looks like this. It's like the little bullet thing from Super Mario. And it looks like this. Here we go. We bring in the A, we bring in the B. And so now, coming out of this, it's going to be not A and B. I hope you see that, and I hope it's not too bad to follow. First we negated the A, we have not A now on the rest of this wire. It's coming into the AND gate, which is going to AND not A, therefore, with whatever's coming in on this wire, which is B. Okay, that's the idea. Okay, now for C and not D, so I think you know the name of the game. D needs to get negated so that we have not D coming out here. And then we're going to AND it with C in another AND gate. Dun dun dun. And so suddenly we have C and not D sitting right there. And then finally, once I have both of these, which we have now made, I can OR them together. You see that? So now I make one big circuit that does the whole thing by adding an OR gate here. Okay? So that's my best way of drawing this OR gate. That's what it is. And now I bring in these inputs, and its one output from this OR gate is the result. It is not A and B ORed with C and not D. Okay? And this probably seems all high level and weird with letters instead of real things, but imagine that this output is something that you care about, like it turns on your light bulb. It makes your Roomba start, okay? Something like that. That is what we can do with these circuits. All right, and so that's where I want to stop for today. I'm going to come back in the programming lecture and we're going to talk about fancy things there, but we'll continue with binary in the non-programming lecture next week. So I will see you there.